Right, with problem number 11 here, we have a radical, and you may want to try to rationalize when you see the radical, but this is not our typical type of rationalizing problem for limits. If you look at number 12, that's a little bit different. You have a radical x, or square root of x minus 3. Here, your denominator in number 11 is just square root of x minus 9 as one expression. So if we were to rationalize that, we'd have to multiply top and bottom by square root of x minus 9. And what that would give you in the denominator is simply x squared minus 9. But when we plug in negative 3 into x squared minus 9, we're still going to get a 0 value in the denominator. And in the numerator, we don't have anything to cancel out there. We don't have any way to cancel something out, and x squared minus 9 in the denominator. So that approach is not going to work. Well, first of all, we may want to look at this and note that if I were to just plug in negative 3 into the numerator, I'd get negative 3, whereas if I plugged in negative 3 into the denominator, I'm going to get 0. So this is not the indeterminate form that we're looking for that we should use other analysis with. This is clearly going to be a vertical asymptote here at the value of x equals negative 3, and also at x equals positive 3. When we have a vertical asymptote, the only thing that we're interested in with a one-sided limit is which direction is it heading. And so as we choose a value, what we need to do then is choose a value for x that's approaching negative 3 from the left. So if it's hard to think of one, just draw a simple number line. Approaching negative 3 from the left might be something like negative 3.1. We know that when we square that value, we're going to get something greater than 9. Minus 9 will be positive. Square root of a positive number is still positive. So my numerator will be negative, but my denominator will be positive, which means the result will be a negative infinity. So if I know I have a vertical asymptote and the numerator is negative for a small number close to negative 3, the numerator is negative and the denominator is positive, then my limit will be negative infinity. With number 13, we have this absolute value of x over x, which you should begin to identify. And we want to find the limit of that as x approaches 0 from the left. Again, there are a number of ways to think about it, but if we just pick some numbers that approach 0 from the left, so for example, negative 0.1, and we plug in negative 0.1 for x, the numerator is going to come out to be positive 0.1, the denominator negative 0.1, so we'll get a ratio of negative 1 there. If we move even closer to 0 and put in negative 0.01, sorry, I had my signs off there. The numerator should be positive because it's absolute value. The denominator will be negative because that's just x. So as I get even closer to 0 with negative 0.01, the numerator again will come out positive, the denominator negative, but they'll be the same value, and so we'll get a negative 1 again. And this goes for all values of x as we approach 0 or get closer and closer to 0 from the left. And we're only interested in the left-sided limit here, so that limit will be negative 1. All right, with problem number 17, we want the limit as x approaches 3 from the left of f of x, and we have a piecewise defined function there. And all we really need to do is to look at the branch that is used for x less than or equal to 3, and so that would be the top branch. And since that's a rational function and its denominator is 2, that will be continuous everywhere. And since that is continuous everywhere, all we have to do is plug in 3 and we get 5 over 2 as the limit from the left as x approaches 3.